Right?
Yeah, okay, I can't do 1 o'clock.
Yep, so we're doing 8 AM.
11, what about 11 AM?
No,
What?
not 11.
11, oh, that's a whole an hour. That's a whole an hour. Oh, it's like a whole an hour.
Why now? I don't want to do,
Why can't I
want to do an hour and 15?
Like,
Oh. Yeah, if we understand.
Well, it's numbers now, it's just make it 5 million.
Still. So it's still rather, this is the new dinosaur.
that's a new game. What? They upgraded for sure. No. This is absurd.
Nope. My internet didn't have connection.
Oh,
If I go here,
Anybody's on the for tomorrow.
Yeah, I didn't know how to do 8. Eastern Sweden was right.
so the.
For what?
So I'm not connected, right? So you're not connected. Want to play a game?
Morning in progress.
Oh, you. That's really helpful. Thank you. Yeah, but we didn't learn. Oh, is this the actual textbook solution?
Yeah, no, I don't think the textbook solution. I don't trust it.
Oh,
Oral
It's okay.
acid, H2,
It's okay.
reciprocate.
It's a little TV series. It's more interesting than the.
Plus, but it's not
actual
analogous
Perfect, that's great.
with Li.
Oh, God, I look so tired.
That's the question?
That's the
No, that's
answer.
the answer. We didn't learn that. We should have learned that. You need to get enthusiasm. Oh, we're supposed to know that.
No, it's because it's like, because when I heard like the textbook too for they did fractional for the like, you know, it's like which you do it like on the fractional.
So, I just don't have energy to play games. It's open card. By the end of the meeting, try to feel it. Do your best understanding. It is formulated in a way to bring quantum to the kindergarten. So there are four empty boxes and there are 4 objects at the bottom. So you can just copy paste or connect them by lines. If you know what to do, if you don't, you can wait on. Too easy task. You're really ready for the course.
I don't know about that.
For you, that's 15 seconds.
Oh, wait, language.
Yeah.
Language.
Pecan class.
You could.
Yes, but.
So let's probably go through slides, and if needed, we will go back to the interview style.
It's just learning solution.
I think it's gonna standardize.
So here's a plan from previous years. We need to do normalization first, excited state, and soon you'll have presentations on the wave packet flows. That's not much different from what others did. The new thing. Yeah, here is this. Special thank you, extra credit to Emma. For taking my job to I need to stop recording because I wanted to say joke which is not for the recording. This is Mr. Share. Okay, so here are the things that you more or less volunteered by, so to say, free will. right? At least elected the least evil, right? And the stuff by Kaiden and Gert are completely new. Other things were in previous years, right? So on Thursday night, midnight, from Thursday to Friday, I expect your slides. Since we are 9 people for 50 minutes, it cannot be longer than 5 minutes. 4 is better. And then leave a minute for pleasant questions, right? I will do my best to cover everything. I will just minimize jokes and focus on the material on Wednesday. And if someone needs more materials, send me an email. I just do not want to dis-navigate your creative part of your brain by throwing in too much extra information, but you feel lost and you need extra information. I have tons of it. So there are, as you noticed, only homework 6A and B. So about a sentence in a Word file by coming Monday. Basically, it is a way for me to make sure that others in the class are listening to the presenter on Friday. So it is, you don't need to study those things. You just summarize, you look through the questions and see if a presenter gives an answer to it. If you think that certain presenters should have answered, but didn't, I have a question. How to answer this question? This stuff, okay? And like, do not worry, do not panic. It's not designed to torture or put in danger anyone's grades. It's just a way of feedback, so that we avoid a situation when I have presented my stuff and I fall asleep. I don't care what others are speaking. Sorry for this little psychological trick. On coming Wednesday in 9 days, please complete little homework. It can be same or a little more amount of writing, but neither of those are intellectually challenging. I saw that you're able to do quiz in 15 seconds. Then this homework with everyone who passed Calculus 1, well, maybe not 15 minutes. Please start doing it a little earlier than the last 15 minutes, but easy. The thinking and implementation and connection of this little mathematical exercises to our class subject is much more important. The exercises themselves are very, very simple. And the content of today's class will be very simple. I do not know how to expand my story for the exercise that can be done in 1 minute. So just my little self-excuse, if I will put more and more material, each of which is 1 minute mathematical exercise, we will lose track of the meaning of the material. It's better to keep a little bit of math and more of the discussion, so that we know how it is related to natural sciences. Because exercises are childish. For anyone who got C in Calculus 1, it is and B and A, of course, it will be so much simple. So nothing to fear. A diagram. Browsing in a space of ideas, right? I should have copy pasting it, rolling from part to part from previous. It's from previous years when I wasn't advanced enough to type it, so it's handwritten. But you recognize it in the same. X-axis are methods, Y are models, and Z is external perturbation that we will touch on maybe last 2 lectures. So we are going in molecular vibrations and harmonic oscillator. We have formulated time-independent Schrödinger equation, and we do we have met. We have been introduced to other operators, and they are expected to help to solve the equation, right? They basically already help. We wasted about 1 or 2 lectures on discussing on the physical and chemical implementations of oscillations, right? And here is, so I will do a little recall, recitation, and then to go into a new material. Again, please be encouraged, brave, do not fear. You don't need to have your full concentration and tons of coffee, just follow slightly. It's not the hardest meeting, but we need to have it. So last time we have formulated time E-independent Schrödinger equation for harmonic oscillator. You're right and wrong at the same time. So any wave, continuous wave function is a wave, but if you tell it for a stranger, it could be deceptive because we are speaking on molecular oscillations, which are just one oscillator, just ions elongate their distance. And then we yes, so it was wrong on this side, but you are correct that since we are quantizing, it is wave. Make sense? So oscillating molecules, if they're light enough, like proton, quantum effects are substantial, and then we have kinetic energy as usual, and for potential energy it is proportional to elongation from equilibrium, quadratic function. Right? So kr squared over 2, and then we introduced mass and frequency to do it in a little more reasonable units. Yes? Okay. How do I feel this table? We were introduced, we have started playing with harmonic oscillator and going forward and then return back. And we are trying to replace traditional Hamiltonian with kinetic and potential energy by product of creation and annihilation operator, because we go up and down, or down and up, but we stay at the same level. Since it is product of linear in each of the basis functions, position and momentum, if you take it squared, we can arrive to position squared and momentum squared and set up coefficients in such way that the cross terms R, P, PR will cancel each other, right? The value of these coefficients were obtained by solving an equation that A dagger A is equal to Hamiltonian. Something, right? And then one has solved for this coefficients. But I would re-solve these equations over again if I am placed on the inhabited island and I need to find them. But it's probably a little easier to memorize them and have some logic in their existing shape, existing form. So the product of weather operators is set up to be dimensionless. So that to get energy, we need to multiply it by energy factor. If their product is dimensionless, each of them should be dimensionless as well. So we need such factors that being multiplied by position and momentum will cancel them. So a factor in front of position should be inverse of distance, and the factor in front of momentum should be inverse of momentum by their dimensionality. H bar by dimension is momentum times position. Right? I need to stop once again. Yeah, I did show nothing. So position and momentum dimensionalities are the same as dimensionality of Planck constant. You've got a good illustration. So you see that each of this stuff has square root of Planck constant in the denominator. Right? What else? Momentum itself. I'll speak about just about the front part. Frequency is 1 over time. So we have mass times 1 over time times position distance. We'll take care of the square roots a little later. So if we combine mass 1 over time and distance, distance over time, it will be like velocity, mass times velocity will be like momentum. So it's still my job to show where square roots came from, but you see a connection. You combine these factors with position, they convert into something like momentum, and then they are divided by Planck constant, giving it dimensionless. Okay, and we will work through details over again. It is not that I will never, if I need to take an exam, I will never tell it. It's just a way to get acquainted with how symbols are arranged in this equation. We did exact way how to derive and find them last time. So, yeah. So how should we do it? Why should I waste my time? I have congenial people in the audience. There are 6, well, 4 of you will comment and just try. And if you see that something is wrong, correct. I think it is a better investment of time. Spencer, you are sitting closer to the exit. You feel free to stop by and. Oh my gosh. So you can either fill the box or connect symbol at the bottom side of it. Okay, yeah, let's. If by mutual exclusion, it will be very strange to have mass and frequency in the power of something as a power, right?
So you got this.
Oh. It tortures me. Can you explain why?
No, I have no.
It's just your scientific intuition.
Yeah.
Okay, let's thank Kairon for.
Yes.
So we already done with 1/2. We're done with this factor. So you have, even if you do it blindly, you have 50% of success chance. Any way how you want to justify, explain? Try something.
Ask. Oh, wait, like why that goes there?
Yes.
What is the R operator again?
Position,
Position?
distance.
Okay. Well. Okay. So I really don't know how to describe it very well. I just know where it goes. That's.
But see, if you put this one in here,
Yes.
then the only one remains here. So courtesy, you will not go to the board because the answer is trivial. Now, if we want these things in the brackets to be of the same dimensionality, right? And then it will be compensated by outside stuff.
Okay.
So momentum is mass times velocity.
Okay.
And if we do omega is inverse times. Is 1 over time.
Okay.
Or 2 pi over time. So distance over time is same as velocity.
Oh.
Mass over velocity is same as momentum. And then we have same dimension.
So that is just like the inverse adding with the momentum?
Yeah.
Okay.
Okay?
Yeah, I kind of got it now.
Yeah. So many thanks to all people. Oh, there are some corrections. So 15 seconds were not perfect. So we will need to get this stuff over and over again, but if you have an idea of this coefficients, it is a good investment in your future, at least for this class. Yeah, but thank everyone who went to the board.
Hold on. They're next, the back row team.
Yeah, you're next.
Okay,
I think Curtis is.
now. Oh, it is the last thing of recital, and then we actually start the lecture. The mathematical content of the meeting is 1 minute long. The rest is my non-confident mumbling, trying to convey the concepts. Mathematically, we came to the, well, it's not kindergarten, but it is a first seminar freshman Calc 1. So last time we did apply annihilation operator to the vacuum. Vacuum is like worth nothing, ground state. And we agreed that it is senseless philosophical construction. Trying to remove an excitation from vacuum, you get nothing. It's not allowed operation. So we got, instead of wave function, we get 0. And by applying this operation, solving differential equation, we've got the Gaussian wave function, e to the minus r squared. And the rest of coefficients came just by playing with constants. We didn't specify the normalization factor. And now there is a question, who needs normalization factor? I imagine myself easily on the other side of the hey James, you missed only the introductory moment. All mathematical part will be with you. So who needs normalization? You may think, okay, it's another tool to torture us young brains. It's only one useless mathematical detail, right? I see from your eyes that you're welcoming this idea. But anyone wants to oppose this? No? Thank you for being fair. But what is the necessity of normalization, which for natural sciences, for the discipline, what will fail if our wave functions are not normalized?
You gotta look at each one in terms of its maximum value instead of looking at it in terms of one.
Yes, but even more important, this is correct, that there is a final ultimate failure if we do not normalize our wave functions. Yes, if you take probability distribution out of non-normalized wave function, can be easily bigger or smaller than 1. If you do orthonormality or orthogonality of non-normalized wave functions, we can get stuff which is not 0 and 1, so bad functions. any expansions and for predicting future, but we can forgive those things or fix them. There is something substantially worse. So if we target to predict an outcome of experiment, what do we do with operators?
Good expectation value.
And if we use non-normalized wave functions, what would be with the expectation values?
Weird.
Yes, they will not agree with outcome of experiment. So one needs to normalize, divide with. If you know that your function is not normalized, then you need to divide your expectation value by convolution of Bryan-Cat to reintroduce normalization. But it is critically important if you want to predict expectation values. And here in the oscillator, in molecular vibrations, we want to predict elongation of a bond, right? If our wave function is not normalized, we will fail. We will show it like longer or shorter by orders of magnitude, which our clients from experimental community will not accept. So you gave us a bad theory. No. If wave functions are normalized, theory is good. Okay. So how do we find this n coefficient? We need, here is the wave function, and we need to normalize it. What do we do? We need to, wave function absolute value squared should be 1. So we need to like square this wave function, integrate, and then solve for n, right? And actually, we are starting lecture now. Here is at the end, we will need to get the equation for the first excited state, which will have 1 plus, minus, and will look like a function with 1 nodal point. And we have much more time than one needs to derive this the function. Okay, normalization first. How do we do it? A little better slide. Yes, this one. It's first 30 seconds of non-zero information, and then will be another 30 seconds. I was thinking about inviting you guys to the blackboard and deriving it, but it's too simple for you. I know you can do it like a snap. I even do not know how to split it between people. So maybe you can just glance on it and tell your opinions, questions, explanations, how to. What is the logic? What do we do, and how do you solve for n? And I introduced the index n naught because normalization for ground state, for first excited state, for second excited state can be slightly different, and we will make a big deal out of it. They all are normalized, but the normalization factor will be slightly different. So what is going on here? Gert, you are supporting the idea that normalization is not needed. It will be especially interesting to learn your opinion about this procedure.
Which part are you asking about?
So we need to find n naught. Right? Close the eyes. I'm going to flip back several slides. And they are quite useless. Waste of your and my time. Yeah. So here is the wave function. We do need to find the normalization factor. What would you do?
So you said that it being normal means that the square root of the absolute value of the wave function has to equal 1.
Yes.
So,
Was one of the useless slides, but we will discuss the next one. So I'm just illustrating wise words of Garrett. So he told that wave function squared upon integration must be equal to 1. Let's apply. Yeah. Right? Yep. Absolutely correct. Curtis, maybe you can just comment transition between these equations. Well, you want to comment, right? It's even better.
Is that what you want me to do? You said comment.
Just give some words. This simple equation really deserve energy that you spent on working.
So if it was a square root, then you would square this both sides, then n would be squared then, right? And then the square root would be off of the function.
So the only you didn't say anything wrong, but I want to hear a transition by plugging in this one into here and there, and how do we get this little ×2 when going from this equation postulated by Garrett to this equation, or we have explicit plugging in the phi naught function.
So the top one goes into the second one.
Mm-hmm. Yes.
Okay.
So at the top we have n to the first power, right? And then if we multiply the function by itself, then if you have n into the second power, right?
Yeah.
Now here we had exponential to the power r squared over 2, right? But we multiply it on itself once again. Multiplication e to the power a times e to the power a equals to e to the power 2a. So why do we have the factor 2 here? So it's just the rules of multiplying exponentials. Do you approve this this equation, or you have some questions with it?
I prove it.
Okay, but thank you. Okay, now we need to take this integral. Right? Question to James.
Yeah.
How would you, and the factor 2 you'll cancel. Here and there. So how would you take this integral? What do you practically, if it will be a little assignment in calculus 1, how would you take this integral? What do we need to do?
Well, what you can do to start with is split it up. So instead of r squared and then all that stuff behind it multiplying together, just split it up as to the power. You can do that because you have to split it up as to the power.
Do you remember what is integral e minus x squared dx?
So that's square root of pi. I'm just trying to figure out what to do with the constants next to the r.
Okay, this is absolutely correct statement that I wanted to say, and James helped me. So we need, I'm just translating your words. We need to bring this integral into this form, right? We need to find such substitution of variables that in the power of exponential, we will have new variable squared. So instead of m omega over h bar r squared, we will have just some psi squared. And then we will have d psi, but as a price of substitution of variables, there should be some constants.
No, well, you can just substitute that. Whatever the weird funny symbol is negative m omega, or just m omega over h bar r.
Funny symbol squared is equal m omega over h bar r squared, right? And then funny symbol is equal to square root, right? And then if you have d psi, it is connected to dr by this constant.
Well, you have a dr in the square root, that's not really.
It's just my ugly writing. This if you come and try to draw on this touch screen, you'll see it offset by quarter inch. So you need to just blindly write, otherwise it will be like smiley face will be like this way. Okay, let's thank James. So we are following instructions from James. Oh, and everyone in the room. So we funny symbol, the linear connection, forwards and backwards. If you go opposite direction, we just invert stuff under the square root, right? And then if we need to express dr in terms of d psi, it will be this inverted stuff, h bar or m square root. So we are replacing dr by d psi, and as a price for this trick, we put a square root up front, right? Now, under integral, we have a thing that is confidently a square root of pi. And then we do have an equation that has fundamental constant square root of pi, and it is unsolved and not squared. So Emma, how would you solve for n not squared? Just give us strategy or the answer or any kind.
Just provide the rest of it over and then just take those.
Yes, okay, so let me try to follow her instructions. So 1 equals square root of h bar, sort of my calligraphy, and omega times square root of pi, and not squared. And then I do invert. So mass, frequency, h bar times pi, square root equals n not squared. Do you count me as a good student of yourself?
The best.
Ah, thank you. Touched. So what do we do next if we need to find n naught?
Square root,
Square root of what?
both sides.
Square root of square root. So it will be if you put here 1, we need either draw another square root or write here 1 quarter, right? So normalization factor is square root of square root, or square root of quadratic root. Yeah. Thank you. Let's thank everyone for strategic. So we do have a ground state of harmonic oscillator, quartic root, and then Gaussian function. Now, one of the questions in this CUE homework for next Monday is asking to compare initial wave functions for wave packet code that we hope to hear from Ifani, and this ground state of harmonic oscillator. Do you see any differences? Do you see any similarities? they should be identical, especially if you would apply the code to harmonic oscillator. So we select, there is a Gaussian wave function, normalization factor, and you saw, I think it was a question of James, why there is a power of 1/4. Last Wednesday, when we looking for like psi not variable, you were asking why there is a power 1/4. Now we get a little more confidence in this, right? Good. Okay, so we finished 50% of our lecture material. Now we need another 50 minutes. We still have plenty of time. It is 30 seconds exercise. I'll just expand the pleasure for whatever, 5-7 minutes. And you agree, I wasn't lying. Previous exercise was doable. We wasted about 2 years of our time getting more and more education. We can get this material just with freshman calculus. Right? So we have a very powerful tool in our hands. Those are ladder operators that help us to browse between quantum states. And if we already know the ground state, we have an equation for it, and we believe that ladder operators are designed in a correct form, then by application of the raising creation operator to the ground state, we should get the first excited state. If you disagree or have any doubts, let me know. I'll be happy to chat and waste time on justifying it.
What's the C1?
Coefficient that we'll get, I should call it N1. We need to get normalization. If phi naught and phi 1 are normalized, simply acting by creation operator on ground state, we'll get not exactly the first excited state, but it will inherit a constant. And the constant will be depending on the pair of orbitals. 2-3 lectures later, we will focus on it, and there will be a recursive formula that for each pair of orbitals. So therefore, we manually normalize them, because by applying creation operator to lower state, we get non-normalized higher state. But the connection will be a simple function, something like square root of n+1, where n is number of the function. We will derive it, and it will be a big discovery. We just look forward to get it. Thank you for the question. So, what are we doing? We are plugging in normalized phi naught, right? It is what you strategically derived. And we are putting the raising operator that you have just filled in your, you can use your quizzes as a cheat sheet for this exercise. Okay. So next, we do want to do it not in abstract algebraic form, but in literal differential form. So we need to replace momentum by its definition. I h bar derivative over coordinate or position, right? So that's basically it. We plug it in and then apply this combination of independent function derivative to known function. And the result will be our first excited state. I don't know if I have nice writing. Okay, maybe this one is the nicest writing I can provide. Sorry, but I will calligraphy. So we put the normalization factor up front. We inherit the 1/4. we put factor that was in front of the creation operator also in here, and in order to match 1/4, we put it in a square power. We may make sure that this prefactor is set up in a correct way. If you want, we can take care of it. If anyone finds an error, you'll be extra credit. And then in the brackets, we do have the independent variable, and we have a derivative over space. Imaginary unit did disappear because we have one imaginary unit from definition of momentum, another imaginary unit from definition of creation operator. And when they fuse together, we come to real, right? So in the first term, we just multiply linear function times Gaussian function. In the second term, it's my last chance to ask questions during today's meeting. What happens if we take first order derivative of the exponential with second power of independent variable?
Times that variable comes down along with all its coefficients.
Right. 2 times independent variable comes down, coefficients comes there, and the function itself is unchanged. Please support or express concerns. Okay. And then if we carefully look onto factors, these 2 and these 2 cancel. But then we can identify that there is a H bar here and there cancel. And then we suddenly identify what a big surprise. Up front, we have mass, frequency, and first power of the position. Here we have, after cancellation, we have mass, frequency, and first power of position. And this minus T minus will give, the sign will be the same. So we will have absolutely the same terms. We just need to factor 2, right? So all stuff with square roots are constant, and then linear function times Gaussian wave function. How do we interpret it if you want to draw it? So Gaussian has a hat shape, linear crosses 0, and where both of them are plus, product is plus. Where one is plus, another minus, product is minus. And it is 0 at point 0. So it is negative and positive, and vanishes on exponential. So one nodal point. Right?
Where's the line coming from?
Which line?
The red line. Where, sorry.
R stands for red. Convincing? So R as function of R. So we multiply one function times, I don't have green in this color palette, times exponential.
Yeah.
Green for Gaussian.
Yeah, that makes sense.
R red, G green Gaussian, multiply, and then we have first excited state. Later on, you may want to normalize. People love to plot them on the simultaneous the energy and wave function. You'll see this image on title pages of most textbooks of quantum theory. You'll see, if you haven't seen it, you will see it. Maybe I will. So please give me a favor. Meeting is done. Everyone is welcome to disconnect. Looking forward to see you on Wednesday. I'm going to collect. Yeah.
Well, we all got the right answer, so we don't really need names.
Well, if anyone will check my performance as an instructor, I need to justify final grades.
Yeah.
And here's the file of grade it works. It works so nicely.
That's it.
Look at this.